Ladies and gentlemen, we're doing chapter 5, section 8 today. We're going to do definite integrals again, just like we were doing yesterday, but they're going to have an application. We're going to have to interpret a situation. And what that really means is it's important what our integrand stands for. Well, like, what is the function in here? What is the meaning of that function? And this is where I was saying that a definite integral can be many different things. Like the answer is not just an area of like square centimeters or square meters. It could be anything. Okay. Now the first example we look at is going to seem kind of familiar, and you're going to maybe think, well, that's what they all are. They're all about distance and velocity and all that kind of stuff. They're not. There could be anything. I just want to say it again. The integrand, how it sets up or what its meaning is, will determine what our answer means or what problem we're solving. Okay. So this first story, this first example is the equation here represents our speed, our velocity. We're driving on a road trip, and the longer time goes by. So down on the x-axis, I'd like you to put a little sketch down. Down here on the x-axis, I want you to put hours. Okay, so this is our time in hours. And then over on the y-axis, I want you to put velocity. Okay, so this is our velocity, and it is in miles per hour. Okay, so let's put down mph, miles per hour. And let's see, what else do we need? We could label this v of t right over here. And one of their questions is something like this. Draw a narrow vertical strip on of width dt. Okay, so draw a narrow strip of dt. So this is time down here, right? So what they're saying is let's make some little narrow strip. We'll call that dt right there. And they want us to draw a rectangle. So, do the best you can. Just draw a rectangle in here. All right. And I don't know if you want a left-hand rectangle or right-hand rectangle. It doesn't really matter right now. Okay. We're just trying to get a visual of what's going on here. Now it says, show a sample point TV on the graph within the strip. So what they're saying is like where you think your rectangle hit the curve, let's put a dot there, and we're going to say that spot is let me put it the way they've got it here, T comma V. Okay, let's see if that makes sense. So I've come over some T spot right there. That's my T. And then I'm going to go up some V amount. Okay, so that makes sense to me. Approximately what distance dy does the car go in that time interval dt? Okay, so what they're saying is how far, if this rectangle meant the distance, which I think it does. So what we're saying by making the top horizontal is we're keeping a constant velocity, right? So what is this velocity that we're getting right here? Well, that would be v of t, wouldn't it? And then for how long are we doing that velocity? Well, some dt. So if I do v of t times dt, that should equal some small change dy. Okay, so what does dy stand for? dy stands for a change in distance. Oops, I forgot my e. Change in distance. Hope I'm making that clear. That's our change in distance, because if we had a velocity for a certain amount of time, this narrow little strip right here would mean how far the car went. Okay, so now they say the total distance a car goes in time from A to B. So now they're saying there's an A over here. Let's say this like at 2, it's A. And then over here, let's say it's at B. Okay, so they're saying the distance from A to B. And they got a little picture. I hope you're looking at page 237, right? And it says in that, let's see, is the limit of the sum of dy values. So they're saying if we added up a whole bunch of dy values from A to B, if we drew a bunch of rectangles in here, the limit of them, like infinitely many of them, would be the distance that the car goes. Okay, so that is y is the integral. So our overall distance that we go, y would equal the integral of dy, right? Isn't that true? If we take the antiderivative of 1 dy, don't we get y? And so we're going to take the antiderivative of v of t dt. So this right here is the integrand. What is our integrand? It's a velocity. And when we take its antiderivative, we're going to get a position, and we're going to go from A over to B. So let's put some limits on that. We're going to go from A to B. And if we add up infinitely many of those strips, it's going to be a distance that the car travels. All right. So I'm going to try this one with you. It says write an integral and evaluate it to find how far the car goes from time 0 to time 1. So I'm going to make this very specific. Like I'm going to go like y sub 0 to 1. So 0 to 1 is going to equal 0 to 1 of 55 plus 12t to the 0.6 dt. Okay, so we're going to take the antiderivative. Here we go. 55t. You can change them to x if you want, but you have to change this guy dx, okay? But I hope you're like, I can handle t. The problem with the t is sometimes they look like plus signs, right? So that's why I put a little tail on my t down here. Then you raise the power by 1, so we're going to get 12t to the 1.6, and we're going to divide by our new power, divided by 1.6. And we're going to evaluate that from 0 to 1, okay? So the nice thing is sometimes, when we have 0, plugging 0 in, you always want to be careful. You don't want to assume because we got 0, we're going to get a 0. But in this situation, we do, right? We plug a 0 here, 55 times 0, 0 there, we get 0. So we don't really have to worry about the 1, or the 0, excuse me. We don't have to worry about the 0. We have to worry about the 1. We plug the 1 in and we get 55 times 1 plus 12 times 1 to the 1.6. You might say, why are you doing that, Nelson? All of that is just 1, right? I mean, 1 times 55, and this is 1 here. But I'm just making it hopefully clear what the heck I'm doing. Okay, and now let's see, all of that's going to become 55 plus 12 over 1.6. So we might need a little Desmos here. So I'm going to go over to where my Desmos is. So this was the function that I took a picture of, and I'm just going to plug in there what my calculations are, right? 55 plus 12 over 1.6. 55 plus 12 divided by 1.6, and I get 62.5. So the car went 62.5 miles in 1 hour, in the first hour, in 1 hour from, I probably should put that right, from time 0 to 1, right? Because it's going to travel different amounts during different 1 hour increments because our car is going faster and faster. The person's getting impatient. They're getting lead-footed. They're putting the pedal down. They're going to get there like, I don't care if we're going 100 miles an hour. Well, anyways, that's how we do problem number 1. We're interpreting, or we're giving it some meaning based on what the integrand is. The integrand is the velocity. Okay, let's look at a different situation. And this situation involves the area between two curves. Boy, this is going to look a little complex at first. Like I got a blue line and then I got the red parabola, right? So the blue one you can see is my y sub 2. Let me see if I can label that here real quick. So this is my y sub 2, right? And then I've got a y sub 1 right here. So you might think, well, what are these pictures all about over here? When I saw this picture, I thought, we want the area between the blue curve and the red curve. We want that area that's contained between the two, that's trapped between the blue and the red curve. And I thought, there are things in engines that have, shapes like this, like intakes might have a shape that's restricted. And this is called the butterfly valve on a carburetor. And you can see as the butterfly valve pivots, if you've never seen one before, they kind of rotate like this. So there's like a pivot bar right there that it's spinning on. It doesn't spin, but it rotates open and then it'll close down. So this one's opening up and it's going to allow air or mixed air fuel into this area, right? So air is going to flow through this butterfly valve that's opening up, right? And that shape that it's getting there It's not exactly what I'm talking about here, but this is what are the kind of calculations that an engineer might do. So what are we trying to do on example 2? By the way, this is problem number 4 on page 238. So I'm going to get you started on one of your homework problems here. This is page 238, number 4. Okay, so I'm just getting you started. And it says doggone it, it's problem number 5. I have the wrong number here. My bad. I'm not making my video again, okay? So this is problem number 5. Let me put a little slash through this and just put a 5 down. Okay, so it says we're supposed to show the region bounded by the graphs of that and that. A thin strip dx is shown in the drawing. Okay, so they draw a dx kind of like right here. I'm going to try to draw a little rectangle. I'd like you to add a little rectangle into your notebook. Okay, and it says there's some point x right here. This would be, like if we're at some x value right here, then this down here is x comma y sub 1. Okay, so this is x comma, that's a comma right there, y sub 1. Why is it y sub 1? Because that's the y sub 1 graph. This is the parabola, right? And then this point right up here, oh boy, I'm gonna draw my rectangle a little higher. Okay, let's say it's hitting right there, right above x. Okay, that point is x comma y sub 2. All right. Now, how would I figure out the distance between y sub 2 and y sub 1? Well, let's just come up with some numbers to make our lives a little bit easier. This one looks like it's about 1, 2, 3 point, I don't know, 3 point, let's call it 3.6. Okay. And this one down here looks like it's at 1, 2, I'm going to say exactly negative 2.6. Yes. Okay. So what is this distance from here to all the way down here, right? How do we do that? Well, here's what I'm going to do. I'm going to go negative 3. Let me try that again. Okay, I'm going to go 3.6. It's a positive 3.6 minus a negative 2.6. To find the distance between two numbers, we need to subtract the two numbers. Let's say you just turned 18 and your friend is only 16 years old. Now, obviously, that's only 2 years difference between the two of you, right? So mathematically, if you want to show somebody that's definitely 2 years, you go 18 minus 16. That would tell you the distance between those two numbers. So that's why I'm going 3.6 minus negative 2.6. What does that give me right there? Well, the negative and the negative make a positive. So I could put right below this 3.6, I could put plus 2.6, right? And then we get what, a 2 there, carry the 1. That'd be 4, 6. I think the distance is 6.2, isn't it? From here to there is a distance of 6.2, right? You agree with me? So this, doesn't seem maybe important to you, but we're going to see that is super important, because what I'm going to do next is I'm going to set up my integral. If I want the area between the blue and the red curve, I'm going to set up my integral with y sub 2. Okay, let me put this down here. I'm going to go y sub 2, and I'm going to do minus y sub 1. Now, why do I want to do that? Well, because what was I doing right over here? These two numbers, where did they come from? Well, my 3.6 came from my y sub 2, and my 2.6 came from my y sub 1, didn't it? Let me give myself just a little space down here. I'm going to write some things down right below here, okay? So this guy right here is my y sub 1, and this guy right over here is my y sub 2. And if I subtract the two, I have the height of that rectangle. That equals the height of that narrow strip. I'm going to call it a rectangle, okay? The book's been saying a narrow strip, but we're drawing them as rectangles, right? So that's the height of my rectangle. What is this distance right here? What's the width of the rectangle? Okay, what is the width of the rectangle? All right, I want you to think about that a little bit. What's going on here? Oh geez, how can I highlight that? I'm going to turn my highlighter on and see if this helps, okay? What is this distance right here? What's the thickness or the width of my strip? Hopefully you're shouting at your screen, or maybe not shouting at your screen, but hopefully you're saying that's dx, okay? So if I set up my integral like this, y sub 2 minus y sub 1, okay, I'm going to put some parentheses around this, not that that's essential, but that is the height of my rectangle. Dx is the width of my rectangle. Now, the fact that I got an x right here tells me, this x tells me, I've got to go and look for things that I can substitute in for y's here. That would be in terms of x. That's a fancy way of saying, look, everything needs to be in terms of x. So what is y sub 2 equal to? X plus 2. Okay, so I go x plus 2. All right, so that's my y sub 2 right there. Let me put that in blue right above. That's my y sub 2. Now I'm going to put my y sub 1 down. And let's do minus. Now, this is going to be important. I'm going to put another parenthesis here. Why? Because there's three terms, x squared minus 2x minus 2. So I'm going to go x squared minus 2x minus 2 dx. If we forget this parenthesis right here, I don't think our integrand is going to be set up correctly, because I wanted y sub 2 minus y sub 1. And without that little parenthesis, it's not going to be, the integrand is not going to be set up correctly. So I know I said that twice. That's super important. That's what today's lesson is all about. The integrand, how we set it up, is going to determine what it is that we're finding. If we have a velocity over here, we're going to find a change in position. How much did the car move? How far did we travel? If we have an upper function minus a lower function, upper function minus a lower function, we're going to have the area between those two functions. Now, if we set it up wrong, like if we put the y sub 1 here and the y sub 2 there, it would still come out to be the area between the two curves, but we would have a negative area. And on these particular problems, when we want the area between two functions, we're always going to want it to end up being positive between the two functions. So we're going to take the upper function minus the lower function, and that's the way I set it up over here. Okay, so you just want to make sure that you distribute that negative sign carefully through, add some like terms, and then evaluate the integral. So I'm going to try a little bit of that with you here. Let's say we wanted to find the area between, where they start hitting and where they stop right there, these 2 points right here and here, right? So we'd have to find those limits. So I'm going to go over, I'm going to show you a picture right now. If I click here, you can see the x is -1. They first hit at -1. For sure, you can see that in the picture, right? So we're going to go from -1 right there to a +4, right? So the limits of integration are important too. So I'm going to go from -1 to +4. Let's do a little simplifying from -1 to 4. So I distribute my negative through. That would give me a -x squared. Usually we write the highest power first. This is called standard form of the negative. Usually isn't with the first term, but that's okay. Then we distribute the negative here. It's going to be a +2x plus one more x. That would be 3x's. If I distribute the negative over here, I get a +2 plus another 2 over there. It's going to give me a 4, right? And there's, my width of my rectangle. This is the width of the rectangle. This is the height of the rectangle. Now that I simplified it, this is still that height of my rectangle. Okay, let's take the antiderivative. -x cubed over 3 plus 3x squared over 2 plus 4x. We put our evaluation bar down, -1 to 4. And we evaluate it by plugging 4 into our function, and we get plug the -1 in. Probably the safest thing to do would be to do that on Desmos, right? So let's think about how we could do that on Desmos. This is, our y sub 2. This is our y sub 1, isn't it? Let me move this around a little bit. Oh, excuse me. The blue is the y sub 2. This is the y sub 1 up here. So right down here, we could put something like, we could put another function in there. We could call it h of x, and we could say that's equal to negative x cubed divided by 3, okay, plus, and we've got 3x squared, so 3x squared divided by 2 plus 4x. Okay, man, I hope I did my integrand correctly. And then right down here, we could go h of 4 minus h of -1, right? So I'm evaluating my definite integral using technology to keep track of everything here. And so I get my final answer. Let's see if I can put that right here. My final answer is 20.83 repeating. So 20.83 repeating. Now I've got an exact answer here by putting the repeating bar. If the AP test, they'll take that full credit, but you can put 20.833 also as your final answer. What do we put for units over here? It is an area that we're asked to find between those two graphs, right? But they don't give me any units. I'm not going to put any units down. It could mean some different things here. So we need to be a little careful with that. Okay. I noticed problem 4 is, asking us to do that in part B. They're asking us to do that. And then in part C, it's asking us to do the midpoint Riemann sum. I've attached the midpoint Riemann sum app, if you will, from Desmos to our Google Classroom slide, our Google Classroom assignment today. So hopefully you can find that and use that. Thanks for watching my video, everybody.